GATE 2022 Metallurgical Engineering Question 43. Which of the following statement is true about black body radiation? There are 4 statements. We need to identify which one of them are correct. First of all, this question revolves around the black body radiation. So we need to understand what is black body radiation. Theoretically, a black body is defined as a perfect emitter and absorber of radiation. At a specified temperature and wavelength, no surface can emit more energy than a black body. So a black body is a kind of idealized body which serves as a standard against which the radiative property of real surfaces may be compared. It absorbs all incident radiation regardless of wavelength and direction. Also, it emits radiation energy uniformly in all directions per unit area normal to the direction of emission. So a black body is a kind of diffuse emitter. I use the word diffuse emitter. By diffuse, I mean independent of direction. Okay. So that was about the black body radiation. Now let's look at the statements one by one. The second statement, the total emissive power of an ideal black body is proportional to the square of its absolute temperature. Let us look if this statement is true or false. The term is total emissive power. Okay. Total emissive power of a black body is a sum of radiation that is emitted over all wavelengths, and it was determined experimentally by Joseph Stephen that the radiation energy emitted by a black body per unit time per unit surface area is given by sigma T raised to power 4. Okay, where sigma is Stephen Boltzmann constant, whose numerical value is equal to watt per meter square Kelvin raised to power. T is the absolute temperature in degree Kelvin, and this relation was theoretically verified by Ludwig Boltzmann. So that's why this is known as Stephen Boltzmann law. Here EB is known as black body emissive power. You should note that the emission of thermal radiation is proportional to the 4th power of absolute temperature. Okay, and in the statement it is mentioned the square of its absolute. So this statement is false. Okay, total emissive power of ideal black body is proportional to the 4th power of the absolute temperature, not the square. Let's look at option C. The emissive power of an ideal black body peaks at a wavelength lambda which is inversely proportional to its absolute temperature. To check this statement, we must understand the concept of spectral black body emissive power. Okay, which is the amount of radiation energy emitted by a black body at an absolute temperature T per unit time per unit surface area and per unit wavelength about the wavelength lambda. Okay, like for example, if we are interested in the amount of radiation a light bulb emits in visible wavelength spectrum, okay, then we use this term spectral black body emissive power. Okay, and the relation for spectral black body emissive power, it was developed by Max Planck with his famous quantum theory. So the Planck's law states that the black body emissive power is a function of temperature as well as the wavelength of the radiation, where T is the absolute temperature of the surface and lambda is the wavelength of radiation emitted. Okay, C1 and C2 are the constants. C1 is and C2 is. K is the Boltzmann constant, H represents the Planck constant, C represents the speed of light. Now, if you look at this relation, you will find that the emissive power of an ideal black body, it peaks at a wavelength lambda which is inversely proportional to its absolute temperature. Okay, so this statement holds good. Why? Take a look at this graph. Here you can see it is spectral emissive power on y-axis, wavelength on x-axis. Okay, so as you are increasing the temperature from 100 300, 500, 1000 Kelvin, you will find that the peak of EB lambda, spectral emissive power, the peak is coming at smaller wavelength. Okay, so that's why the emissive power of ideal black body peaks at a wavelength lambda, and it is inversely proportional to its absolute temperature. Okay, higher the temperature, smaller will be the wavelength. Means as the temperature increase, the curve shift to the left to the shorter wavelength region. Consequently, a large fraction of radiation is emitted at a shorter wavelength at higher temperatures. Okay, so option C is correct. Look at option A. Among all radiation emitted by ideal black body at room temperature, most intense radiation falls in the visible light spectrum. See, the answer lies in the curve itself. Okay, here the visible region is violet to red. Okay, this is the lambda for violet, this is the lambda for red. So this is the visible region, and from the curve itself you can see the radiations that are emitted. The most intense radiation does not lie in the visible range. It depends on the temperature. Okay, the intensity of the radiation depends on the temperature. Right? So it is not necessary most intensity will lie in the visible range. So this statement is false. Fourth statement, the radiant energy emitted by an ideal black body is greater than that emitted by non-black body at all temperature above 0 Kelvin. If you look at this curve, on y-axis you have the energy that is emitted by a surface. It is a function of wavelength. On x-axis it is wavelength. So this curve, the curve for black body is always higher than the curve for a real surface. What does it mean? It means that at any temperature, a black body will always emit higher energy as compared to a real surface or a non-black surface. Okay, so the last statement also is true. So option C and D are correct.